Assalamu alaikum. This is lecture 5 of the Control System Engineering 1. We are discussing chapter 2, modeling in the frequency domain. So we already covered first 4 articles of this chapter. Now we actually want to discuss the article 5 or 2.5, translational mechanical system transfer function. In the last lecture 4, actually we discussed electrical network transfer function. So somehow this system is not we are not that used to with these mechanical systems. So that is why it will be always better if you can somehow compare the mechanical system with the electrical system. So we'll try to start finding the analogy, then the method that we are familiar with, like finding the loop equation or finding the node equation. So if we can actually apply those ideas into the mechanical system, that will be a lot easier for us to comprehend the basic understanding of the mechanical system. We know the fact that we are not that familiar with mechanical systems, but still, we are as a interdisciplinary fact because of the fact that some of the mechanical system is inherent in electrical system as well. So we cannot actually avoid those, like in the motor or the generator. So we have mechanical parts as well as electrical output or input output, vice versa. So that is why we actually have to learn this, but you don't have to take too much on heart that these are not familiar to you. Rather, if you practice more, then it will be easier gradually. So we'll start also slowly, and we'll try to see how it can be made a bit easier, even though it doesn't fall in our domain. So translational mechanical system. Translational means actually linear movement. So the system related to the linear mechanical movement. So those are called actually translational mechanical system. Now, as we know that in our electrical system, there are 3 passive components. Okay, so one is capacitor. Then we have resistor as well as inductor. Okay, so out of this, these 2 are actually energy storing elements, these 2. And this one is energy dissipating elements. Okay, so energy dissipating element. Similarly, in the mechanical, translational mechanical system also, we have 3 components. So one is called spring. Okay. So the second one is viscous damper. Or friction. You can also call it as a friction. Okay, so then third one is actually mass. Okay, so similarly, these 2 here are also energy storing element in the mechanical system. So this one kinetic energy it stores, this one actually the potential energy it stores. So energy storing element. And this one, just like in the electrical system, whatever the function of the resistor, there is energy dissipation. So there are similar things being done by the viscous damper or the friction. So the capacitor produces heat, the friction also produces heat. So we have a lot of similarity between the 2 systems. So let us compare the table. It will give you better analogy if we look at the table. So table 2.3 is basically for electrical system, and table 2.4 is for mechanical system. So now if you compare these 2 tables, then look at here, this column with this column. and the coefficients of the spring is K, coefficient of viscous damper is Fv, and the mass itself is M. So these are the parameters similar to our RLC. Okay, so they also have those parameters K, Fv, M. Now, if you compare these two tables, first of all, look at the equation. So voltage is related with current using an integral formula. So similarly, force is related with velocity with an integral formula. Okay, so here voltage and current is related with a proportionally constant. Similar thing here, voltage and current is related by a proportionally constant Fv. And also you have a differential equation. Similar way, voltage and current is related by the differential equation, as well as the constant L in case of electrical and constant M in case of the mechanical. So what analogy we can conclude here? We can say that our force can be made analogous with our voltage in the electrical domain, the reason or the source. Similarly, the current, sorry, it should be on the other side. So the velocity can be compared with our current. Okay, so now capacitor follows similar equation with the spring. So basically spring can be compared with your capacitor. And then you have resistor. Resistor is viscous damper basically. So viscous damper is analogous with resistor. And your mass related with inductor. Okay, so one thing we missed, but that also can be related, charge here can be related with displacement. Okay, so displacement can be related with charge. Okay. So similar equations. So as well as if you look at the impedance here is obtained from this. Basically from this equation here, which is actually a modified, this equation, this column is a modified version of this one. So obtained from this one. Similarly, this column is a modified version of this one. Okay, so the velocity is the rate of change of the displacement. So from this one, actually, the impedance is being calculated. And if you look at the impedances, they are actually similar in some sense. So, but even though it seems a bit different, but don't worry. If we derive it from this equation, it should be similar. So to make the things identical, actually, we go for the displacement, this column instead of this velocity, force velocity instead of this column. For finding the impedance, we go for this one. But in electrical, they have used this one, so they have obtained the impedance from this one. So we can also do the similar thing from here, but in that case, you have to use the charge. So charge and the voltage relationship doesn't give you the impedance. Okay, so we have just used impedance, even though in reality, the impedance should be from the fact that it has to be voltage by current, so basically force by velocity. But for our ease and to make the equations easier, we just assume that ZMS is actually Fs by XL. So this is just another assumption, but eventually it is not true. Just to make the equation easily obtainable, we are assuming this thing. So you have to clearly understand that. Otherwise, a full analogy cannot be taken. Okay, so this is if you are interested about the mesh analysis. then this assumption is good to go, because the equation that we are taking here is actually similar to the voltage in a loop. So that will help you to take the analogy of mesh or loop analysis. Loop analysis. So one thing we also can do is we can compare the same column in the mechanical one, so this same column, but in the electrical, this column in the reverse direction, so say in this direction. So what we are going to do, we are comparing this one with this one. Then the middle one is always same because it is energy dissipating component. And then we'll be comparing the third one in the mechanical with the first one of this column. So this is what you have to do. So now, as you can see, the first column here, the force and the velocity related with the integral formula. So here, current and the voltage is related with the integral formula. So what analogy you can make now is basically your force. It can be analogous to current, which is the source in case of nodal analysis. Then second one, also your velocity will be analogous to your voltage. Okay, then the third assumption, displacement, also you can take. Okay, so component wise, what will happen? Component wise, basically, now in the reverse order, basically. So spring will be analogous to mass. Spring will be analogous to inductor. Then your viscous damper will be analogous to your resistor. It is always same, it's not changing. Then you have mass will be analogous to your capacitor. Okay, so and when we are going to use this analogy, if you are interested about the nodal analysis, then this will be helpful for us. So if you want to adopt nodal analysis in mechanical systems, so this will be helpful. Okay. So now I'm not sure why, but I think most of us we like to treat the voltage as a source rather than actually current as a source. So in general, actually prefer this one, not sure why. More about this analogy we'll be discussing Article 2.9, but for now on, actually we'll try to go with this one. So more about, so now the first thing is how to apply this. Okay, so first of all, we should actually define, just like the electrical network, we always start with the RLC network. In the mechanical as well, we have similar network, which can be called as so the mechanical RLC network maybe. So, but the mechanical system requires a differential equation to represent it. So in the mechanical domain, we call this equation as a equation of motion. So equation of motion, which is also a differential equation. So differential equation to represent the system. Okay, so how we can describe the mechanical system just like the electrical system. This is our objective, and just like the way we do in the electrical system, we'll try to find out similar analogies so that it doesn't become too difficult to understand. So say we have a reference In electrical, we have a ground. So in mechanical, we have the reference like solid body that doesn't, or solid surface that doesn't move. So this is mechanical reference, you can call mechanical reference. Okay, so something that doesn't actually change its position. Then you have a spring. Then you have a damper. This is a symbol of damper. So you have a damper. Then you have a mass. Okay, so this is called mass spring damper systems. Mass, you have spring coefficient K, the coefficient of viscous damper Fv. Now we are assuming this is the on this mass we are actually applied a force Ft, and from its original position it is having a direction of motion. Okay, so xt. Just like in the electrical system, what you do in a loop, we assume a current direction. Okay, so say we have an electrical system, something like this, and then we have a component, so say something. Okay, so always we try to assume that maybe some other loop is also there, so don't worry about those. So maybe something else is there. But we always assume that the current is going in this particular loop. Always we assume, try to assume a direction like this. Okay, so why this direction? Because we always assume that the voltage source is there. It is powerful enough that the current will be actually generated from that one will be big. So, and the direction is arbitrary as well. Sometimes if your direction is wrong, you will have a negative result. Similar thing here, you have to assume a direction of motion xt, and in general it is in line with the applied force convention. So you can also take the reverse direction if you want, but then if your assumption is wrong, then you will have a negative sign. Negative value will be appearing in your solution. Okay, so this is mechanical RLC network, you can say, or mass spring damper system. Now, how to find out the differential equation here? So this is what you have to do. So for finding the differential equation, so basically you have to find out a positive direction, and then you have to draw one special diagram. They call it free body diagram. I know it's okay, so it seems, name seems a bit odd, but this is how they call it, free body diagram. Free body diagram. Okay, so basically what they do is whatever the mass you have, the m, on that mass you have to assume the force direction, as well as you have to give the direction of the motion like xt. Then you have to find out the forces that is actually applied on it. So if you try to apply force on this mass, it will try, the force will try to drag the object in this direction. So just like in the electrical system, all the parameters actually try to oppose the force, oppose the voltage. Similarly, in the mechanical also, it will try to oppose the direction. The mass itself, because of the mass, it will try to go, it will try to oppose the force. The spring will try to hold it back, and because of the friction, it will also be opposed. So in general, whatever the force, this is the energy supplying component, and these three, just like RLC, they are actually energy absorbing components or passive components. Okay, so energy supplying components, whatever the direction of it, and the energy absorbing components, they will actually, or dissipating components, they will be in the reverse direction. So what you can say is that we'll have a direction in the opposite way because of the spring, say according to our table, kxt. Okay, So next one, because of the friction, you will have FV dxt by dt, and as well as we'll have m d square xt by dt square. Okay, so basically if you look at the table, then we are actually taking this column. Okay, so the force with respect to the displacement, as we already said, for the impedance, so that we can actually use the electrical formulas, we'll be using this one instead of this one. Okay, so force is related with displacement with the K, then force is related with your friction with dx by dt, and for the mass it is md square x by dt square. Okay, so not that difficult. So once you have this free body diagram, what you have to do is you have to convert all this parameter into Laplace domain. Okay, so Laplace domain. So basically this one will be replaced by xs. This one will be replaced by fs. Then this one will be replaced by kxs. This one will be replaced by fvs, first derivative, so s into xs. This is second derivative, so m s square xs. Now, what is the electrical formula in the loop, or the energy balance formula in the electrical domain is summation of the voltage should be equal to 0, isn't it? Voltage in a loop, voltage equal to 0. So similarly, summation of the forces in mechanical also 0. So basically, supplying force should be equal to the absorbing force. So if you apply that formula from the Laplace one, then what do you get? ms square xs plus fvs xs plus k xs equal to fs. So applied force equal to actually absorbed force. Okay, so now take common, it is algebraic equation. So ms square plus fvs plus k xs equal to fs. So if you want to find out the transfer function, then your g of s is output by the input. So basically xs by fs, which will give you 1 by m s square plus fvs plus k. So in the RLC network, can you recall the equation that we obtained in the RLC network while we were discussing the RLC network's transfer function? So just try to recall that. Example, I think, yes, example 2.6. So using your inductor capacitor, the charges equation. So basically, this is equation 2.65. So equation 2.65, you have something like this: LCS square plus RCS plus 1 VCS shows VS. Okay, so from that one, if you find out VCS by VS, then you had something like this: 1 by LCS square plus RCS plus 1. So as you can see, they are actually almost identical. S square is then constant, the constant here was 1. So after deriving the equation or the differential, the transfer function, they look almost identical. It's very difficult to distinguish those. So that is why actually we'll try to uh, take the advantage of our electrical knowledge to figure out the transfer function of the mechanical system. So based on this equation here, so basically this column, based on this column, so that is why instead of writing, making things complicated, we can directly take something like this, KXS. Similarly, this one will give you Fs equal to FVS XS, and this one will give you Fs equal to MS square XS. Okay. So just like, and then you can find out that one formula, that is summation of impedances into the previously it was current. Now since we are finding the analogy for ease of the equation derivation with actually displacement, so basically into displacement will give you the sum of the forces. Actually, in most of the cases, there is only one force in a single equation of motion. So summation of the forces. Okay, similar to the electrical motor. Summation of the impedances into current was actually voltage. So same thing applies here. And now, how many differential equations required? How many differential equations required to represent a system? So if you want to figure out that, then what will be what we need to know? So how many differential equations required to represent a system? That actually depends on how it depends on the number of the linearly independent motion. Okay, so number of equation in the mechanical domain required is equal to number of linearly independent motions. Number of linearly independent motion. Okay, so number of linearly independent motions. So that is a critical thing to discuss. What is linear independence means? So it actually implies that a point of motion in a system can still move if all other points of the motion are held stationary. So what does it mean? If you have different point in your mechanical system, all of them can move, but if one of them can independently move, if the others are not moving. So if you can assume something like this, then it is called linearly independent motion. At times it is also, another name of this thing is also called number of degree of freedom. So degree of freedom. So as you have seen, degree of freedom. Yeah, I know what you may be thinking, that what are their terms, isn't it? Free body diagram, equation of motion, then degree of freedom. So much gravity on each of the terms. But they're actually also present in electrical system, but we keep them simple. We don't take them so differently. So in our electrical system as well, so it's, what we have is superposition. So the linearly independent motion actually implies that whether or degrees of freedom implies that whether superposition can be applied or not. So simple as simply similar ideology of the electrical term is whether you can apply the superposition or not. Okay, so let us try to do try to solve one problem that will actually help you to see whether it is possible to have your finding the how many number of equation you need or how many linearly independent scenario you have. So say we have a system like this. It's difficult to draw on the tab at times. Okay, so this is the reference or stationary body, so it is not moving. Mechanical reference. Then you have two masses here. We are calling this one as M1. By the way, this is your example 2.17. This is M2. In between them, they're connected with a damper and a spring. This one is also having one spring connected here, another spring here. Okay, so this is the coefficient of this one is K1. This is FV3, FV3. This is K3. This is K2. Then you also have two more friction, the friction with this M1 and this surface, that is what is called FV1, and also this one, this is FV2. Okay, so this is your mechanical system. Now both of the mass can move. Say this movement here is x1t and the movement of this one is x2t. And they are saying that a force has been applied here. So this is your Ft. Okay, so this is the scenario. Now, first of all, let us try to explain what is degree of freedom. The degree of freedom suggests, or linearly independent motion suggests, that once this object is moving, we can assume that one can move once this is still stationary, or we can assume that this one can move while this one is stationary. So if this is applicable, then we need two separate equations to write this, describe this system. Okay, so how to do that? Let us try to begin with this example. So again, you have to draw free body diagram for two cases. One case is when M1 is moving. So M1 is moving. Okay, so and number two is when M2 is moving. Another thing you have to specify, M2 is stationary. M1 is stationary. M1 is stationary. Okay, so free body diagram again. So say this is your M1. Okay. So M1, while actually M1 is moving. So M1 is moving because of the force applied on it. So definitely the force will be applied in this direction. So your F will be there. You can directly write without in the time domain, you can directly write in the frequency domain. Okay, so F1 is applied. So Fs, okay, in this direction as shown here. Now, if M2 is stationary, so M2 is also temporarily, we are saying that it is a stationary body, so it is not moving. So what will happen if M1 tries to move in this direction x1? So what will happen? So since it is stationary, what you are going to face is this. Because of this force, you will have some forces in the opposite direction. So this will be this will be produced by this K1 the friction as well. And these two also will try to repel in the opposite direction. So all of these will be actually applying in the opposite direction. So you can say that because of the K1, you will have K1 X1S. Because of FV1, so we can also say that we will have in the opposite direction FV1, the down one, FV1S X1S. X1 is moving only. Right? So as well as you will have two other forces. Now the mass itself will also be in the opposite direction. So M1 S square X1S. Okay, so these two, FV3, FV3S X1S, as well as you will have the K2 X1S. Okay, so this is related to the first one. So we assume that this body is stationary. So this one is stationary. Because of that, if you try to move this body into this direction, so you'll have opposition by this spring, the damper. These two will also oppose the direction of the force. So all of them in the opposite direction, and you have just the force been applied in this. So this is one free body diagram. The other free body diagram, because of the second condition, and the force still on M1. Okay. So what is the scenario now? This one is stationary. This one is stationary. This one is now moving. So if this one is moving, then what will happen? If this one is moving, then these two components, this one and this one, will try to, the spring will try to keep it in its own position, so it will try to force in this direction. Similarly, the friction will also be trying to force in the opposite direction. But since it is a stationary body now, so what will be the force on this stationary body because of the movement of M2? So whatever the force being experienced by M2, the M1 will be experiencing opposite force. The direction of the force will be opposite. So that means if M1 is experiencing a force in this direction, so M2 is experiencing force in this direction, then M1 will be experiencing this equal and opposite force, Newton's law, in the opposite direction. So basically, it will experience two forces because of the movement of the other particle. Mass is basically K2 X2S and FV3 X2S. So what you have to do, you have to combine these two superposition. Okay, so combine these two using the superposition, and then what the combined free body diagram that we are going to get is something like this. Okay, so we can also add for simplicity. So this one, this one can be added with this one, same direction. So we can write K1 plus K2 X1S in this direction. Then the viscous force can also be added. So this one and this one will be added together. So this will also have FV1 plus FV3 S X1S. And then the force in that direction, Fs, and you have mass in that direction, M1, S square X1S. And the other two forces that in the other direction will be two that we derived from this diagram. So that is K2 X2S because of the movement of the X2. So FV3S X2S. Now this is all the forces on the body. So now you can write actually the differential, the equation that represents this one. And the equation will be forces with the same sign can be put in the same side. So you can write something like this. This to the direction here will be one side, the direction to the left will be one side, and then to the right will be another side. We can do that. So start with m1 s square x1s plus fv1 plus fv3 s x1s plus k1 plus k2 x1s equal to fs. Then you have plus fv3s x2s plus k2 x2s. So take all the impedances in the other side. What we are going to get is, and if we just take common of x1 and x2, so we can write something like this: m1 s square plus fv1 plus fv3 s plus k1 plus k2. Okay, so whole thing with x1s minus, if we take these two in the other side, then also take common of your x2, then it will be fv3s plus k2. Then you have x2s equal to fs. Now try to look at this equation. Does this equation look similar to you? So impedances of one loop with the corresponding current. There are common impedances with the current of the next loop, second loop, equal to your voltage. Okay, so similar to the electrical network, two-loop electrical network basically. So can we actually write the second equation? This is the first equation based on the free body diagram that we have drawn. But without the free body diagram, is it actually possible for us to find out this equation for the second one? So basically for the second one, ideally, you should also go for two free body diagram because of the movement of M2 and also M1. Then you combine, then equate, then you should be finding an equation like this one. But my question is whether the analogy that we have developed, that the summation of the impedance of one loop with the current of that loop, then the common impedance and the current of the other loop is equal to the force or the voltage. So that thing can be applied or not. So let us try to apply that idea from this diagram for the second loop. I know it is early days, it's difficult to comprehend, but still let us try. So, and also the thing is similar in the electrical, what you do. The loop that we are considering for that particular load, the sign, loop sign is positive. The adjacent loop sign is negative. So the similar thing is also happening here. So now this is for loop 1 maybe, or x1. So now we try to write for x2 or mass 2. So how can we write mass 2? So first of all, what is common in between them? So common in between them is these two. Basically fv3 and k2. Okay, so write the common thing first with the negative sign because you're writing for the second loop. So fv3s plus k2, this is x1s. Then writing for the own loop. So writing for this particular loop, what will be the scenario? All the impedances, summation of all the impedance and the corresponding displacement. So all the impedances will be basically M2 S square plus, now what are the impedances we have? We have this two spring K2 and K3. We have two damper, that is FV2 and FV3. So basically we can write FV2 plus FV3 S plus the spin K2 and K3. K2, K3. So this is with X2S. Is there any force? No force, so 0. So mechanical network can also be the the equation of the mechanical network can also be figured out the way we deal with the nodal analysis in electrical domain. Okay, so there is two ways. You can always go for this free body diagram comparing the motion of self motion and the motion of the adjacent one. So similar thing should have been where we should have been doing here as well. Two free body diagram and combining those two, finding the equation. Then from that equation, you should have come to this conclusion. But as you know that since we are doing with the analogy, it's really very, very easy for us to directly writing the equation instead of going for that derivation. So whatever the thing that we have, and also from this equation you can easily see this is the common portion. So definitely the common portion will be coming here, FV3 plus K2, okay, X1S, then plus M2 S square plus FV2 plus FV3S plus K2 plus K3. Okay, so this is your X2S, there is no force, 0. So now if somebody asks you to find out the transfer function G of S equal to X2S by Fs. So how to do that? Same Kramer rule. So once the equation is there, it doesn't make any difference whether it is an electrical system or a mechanical system. So X2S will be basically M1 S squared plus terms eventually. Okay, so then in the denominator you have FV minus FVS, FV3S plus K2. Then you have Fs and 0. Okay, so divided by your del. So basically this parameter will be cancelling because multiplied with 0. So minus minus will be plus. So basically you will have Fs times V3S plus K2. Then you have the del. So X2 is already there. In the other side you have Fs. So your X2S by Fs will be actually V3S plus K2 by del. So this is your transfer function of the system. What is del? Del, I think you already know what is del. So, but still, if you want, you can also write what is del. Del is the determinant that you have to find out. M1 S squared plus FV1 plus FV2 FV3 S plus K1 plus K2. Okay, so similar here you will have minus FV3S plus K2 minus FV3S plus K2. Then you have here M2 S square plus FV2 plus FV3S plus K2 plus K3. Okay, so electrical circuit 1, again coming back. So this is how you have to, even if it is a mechanical system, you can actually convert this mechanical system with the electrical analogy and then it will be a lot easier for you to figure out how to find out the transfer function of the mechanical translational system. So look at the example. I already said to you that the more you practice, the more familiar things become and more easier to deal with those. So let us have a look at another example. So again, we have another mechanical system. In this mechanical system, we now have this kind of scenario. We have one mass here, we have another mass here, we have another large mass here. Okay, so now this one is related with spring here, K1. It has a friction here, V1, another friction here, V2. So the friction here is V3. The friction here is V4. Now you have three mass, three linear movement is possible. M1 can move while other two are stationary. Similarly, M2 can move while other two are stationary, or M3. So three linearly independent movement is possible. So we're just assuming that movement of this one is x1t. The movement of this one is x2t. And the movement of this one is x3t. And the force has been applied here. So the force is applied here, Ft. So now you have to write the equation for this particular mechanical system. So how many, we have three degrees of freedom, or three objects who can actually move linearly independent to others. So we actually have to write three equations. So from electrical perspective, three loop we have. So x1, x2, x3, three assumed direction of motion. So let us first write the equation for M1. So x1. So self-impedance. So M1 S square plus what are the common all of its own impedances. So how many FVs you have? FV1 and FV3. So two FV you have. I think I forgot one thing. There should be another spin here. Okay, so sorry about that. Okay, so now look at here. So look at the equation. So self-impedance. This is self. This is self. This is self. This is also self, and this is also self. So your equation should be something like this: M1 S square plus FV1 plus FV3 S plus 2 spring K1 plus K2. So the motion of that one. Then the forces, because of the motion of other one, will be the common in between M1 and M2. So what is common in between M1 and M2? M1 and M2. Basically, the common thing between M1 and M2 is only K2. So minus K2 X2S. What is common in between M1 and M3? FV3. So minus FV3S X3S. Is there any force on M1? No, so 0. So the second equation, how should the second equation be looking like? So for M2, so other one will be actually negative. So minus, which is common between M2 and M1 is K2. So minus K2 X1S. Then the self-impedance. So M2 S square plus how many friction you have? FV2 and FV4. FV2 and FV4. So FV2 plus FV4 S plus then spring, only one spring, K2. So K2 X2 S. And what is the common in between M2 and M3? The common thing is FV4. So minus FV4 S X3 S. The force is applied on M2, so Fs will be also there. Okay, so what about the third one? For the third one, we have to find out the relation between the third one and the first one. Common impedance is this one, already calculated. So minus FV3 S X1 S. The common in between 2 and 3 is this. So minus FV4 S X2S plus self impedances. So M3 SS square plus FV3 plus FV4 S. There is no spring associated with the M3. So this is your X3 S equal to 0. So they only ask you to find out the equation. So finding the equation of the mechanical system, translational mechanical systems now becomes very, very easy. Very, very simple to do. Okay, so this is how you have to do it. Now let's go for, now they can ask you to find out transfer function, any one of them, maybe x1 is by fs, or maybe x2s by fs, or maybe x3s by fs. Okay, sometimes they can also find out, they can also ask you to find out v2s by fs. So you actually have to then figure out the relation between v2 and x2, then you can easily find it out how to do it. Now let us look at one practical example, numerical example that will give you a bit of confidence. Skill assessment exercise 2.8. Skill assessment exercise 2.8, how to find out the transfer function. So now the system is something like this. You have a system something like this. So this is your reference. Then you have a mass. This one is one mass, M2. And you have another mass inside M1. So this is your inside M2, so M1. Force is applied on this one, Ft. You have friction here, Fv4. You have one spring here, okay. You have a damper in between the M1 and M2, so friction in between them maybe. So this is your Fv3. Another friction is here in between 1 and 2, as this is your Fv1, and also in between 1 and 2 another friction here, so Fv2. I think this is all. Okay, so direction of motion. So M2 moving in this direction, and M1 also we are assuming the same direction of motion. Okay, so this is your X1t related to the down one motor, and this is related to M2, so X2t. Okay, so all the parameters, coefficients are actually given as 1, like mass is 1 kg, then your viscous damper is 1 Newton second per meter, then your spring is 1 Newton per meter. So all of them are 1, magnitude are 1. So this is 1, this is 1, this is 1, this is 1, this is also 1, this one is also 1. So all of the parameters also weight, the mass is also 1. So two bodies there. One is this one. Let me use different colors. So this is one body, which is M2. Okay, and we also have another body or mass M1. Okay, so this is another one, and the force has been actually applied on M1. So we have to find out the transfer function. The transfer function they are asking us to find is GS equal to X2S by Fs. Okay, so this is what we have to find. So just like before, let us write the equation first, then we'll try to go further. Okay, so the equation for the first mass or first degree of freedom or first movement, linearly independent movement, X1. So let us write for the first loop. So for M1, let us write using the symbol first, then we'll go for the numerical thing. So the M1, first loop, M1 SS square plus all the friction associated with this one is this one, as well as this one. So 3 friction. So FV1 plus FV2 plus FV3S plus 1 constant K, spring constant K. So okay, so this is X1S. Now, what is common in between X1 and X2, or mass 1 and mass 2, is basically the viscous damper, 3 viscous damper and 1 spring. So all are common. So FV1 plus FV2 plus FV3 S plus K. These are the common thing. So X2, and the force is also applied on basically on M1. So we can write Fs. So now let us write in terms of numerical values. M1 is 1, so 1. These are also all 1, so we can write 3s. This is also 1. This is 3. This is 1. So what you can write is S square plus 3s plus 1 X1s minus 3s plus 1 X2s equal to Fs. Similarly, we have to write the equation for the second one. So for this, what is common? Common thing is not changing. So common thing is remaining as it is. So minus 3s plus 1, common in between M1 and M2, X1s. Now all the impedances of M2. So the value of M2 is 1, so we can write S square directly. So how many viscous we have? Viscous previously we have 3. So 1 here, 1 here, another here, and also this one. So as well as with this reference surface, we have another here. So 4 viscous components. So basically 4s, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 101, 102, 103, 104, 105, 106, 107, 108, 109, 110, 111, 112, 113, 114, 115 and then one spring, so plus 1. Then you have x2s equal to, there is no force. So this is your equation for this corresponding system. Now what they want you to find out is what is x2 by fs. So you have to go for the Cramer's rule, and that is now we are interested about x2s. x2s equal to, so 3, sorry, s square plus 3s plus 1 by minus 3s plus 1. Then we have minus 3s plus 1. Sorry, fs 0. And the del, for the del actually to write that thing, s square plus 3s plus 1 minus 3s plus 1 minus 3s plus 1, then you have s square plus 4s plus 1. Okay, so what we are going to get here is definitely this will be multiplied with 0, and then you have a negative, so you will have fs times 3s plus 1. Okay, so and if you cross multiply, then what you will have is s square plus 3s plus 1, s square plus 4s plus 1 minus 3s plus 1 square. So if you just simplify a bit, multiply and simplify, then what you are going to get is s to the power 4 plus 7s cube plus 5s square plus s. So as you can see in the denominator, s can be taken common. So our function g of s equal to x2s by fs. Then what will be left is 3s plus 1, and then take common of s, so s cube plus 7s square plus 5s plus 1. Okay, so this is the required transfer function. So this was your article 2.5, obtaining transfer function for translational mechanical system. So I tried to go as slow as possible and try to derive step by step. I hope that will help you to understand. So in the next class, next lecture, we'll be trying to see article 2.6, that is rotational mechanical system transfer function. Okay, see you in the next class, inshallah.